So let's start. With a great pleasure, let me introduce our first speaker today, Professor Anatoliy Petravchuk from Taras Shevchenko National University of Kiev. The title of his talk is Module Structure of Certain Lie Algebras.
Good morning. Do you see my screen?
Yes, we see.
The talk is the title of the talk is Module Structure of the Lie algebra W and K over SL and K. Now one can also say over GL and K. Also, in this case, this is the same. This talk is based on results obtained jointly with Igor Chapovsky. Let K be an algebraically closed field of characteristic 0, A the polynomial ring in n variables, and recall that a K-linear map D from A to A is called a K-derivation of the algebra A if the next identity holds for any F and G. Leibniz identity. All K-derivations of the K-algebra A form the Lie algebra W and K or the field K with respect to commutation or taking the Lie bracket. Note that every element D of this Lie algebra W and K can be uniquely written in the form as a linear combination of partial derivatives with polynomial coefficients. And from the viewpoint of geometry, Wn consists of all the polynomial vector fields on K to n. From the viewpoint of differential equations, any derivation D can be considered as an autonomous system of ordinary differential equations. X dot equals f of x. The Lie algebra Wn was studied by many others from different viewpoints. Maximal subalgebras of Wn were studied by Rudakov, Bavula, Bell, Buzaglo, solvable and important subalgebras by Bavula, also Petravchuk, Martello, Makedonsky, automorphism and derivations of K of Xn and related structures by Bavula, Bezushak, Rudakov and others. The Lie algebra Wn has a natural grading. Wn is the direct sum of homogeneous components Wnj, where j is greater or equal -1, where Wnj consists of all the derivations with polynomial coefficients which are homogeneous polynomials of degree j plus 1 or 0. If D belongs to Wnj, then we say that D is homogeneous of degree j. The K-subspace Wn0 consists of all the linear homogeneous derivations. This component Wn0 is a subalgebra of Wn, and Wn0 is isomorphic as a Lie algebra to the general linear algebra GLN of K. Note that Wn0 contains the subalgebra consisting of linear derivations with zero divergence, which is isomorphic to the simpler Lie algebra SLN of K. All the homogeneous components Wn I are modules over Wn0 and also over the Lie algebra SLN K. The main result of this talk, theorem 1, is the following. Every Wn0 module Wn I is greater or equal 0, is a direct sum of two irreducible submodules Mi and Ni. The submodule Mi consists of all the divergence-free derivations, and Ni consists of all derivations that are polynomial multiple of the Euler derivation En, which is the sum of partial derivatives with coefficients xi. As a consequence of this theorem, we obtain the equalities that product of Wn I and Wn j is the Wn to I plus j, except the case when I equals j equals 0. For the case I equals j equals minus 1, this equality also holds if we put Wn to minus 2 equals 0. As an application of the main result, we point out a criterion under which an element of Wn generates, together with the finite dimensional subalgebra Wn to minus 1 plus Wn0, the entirely algebra Wn. And here some technical equalities to prove the main results. And the first lemma shows that divergence of sum or difference of two derivations equals, of course, of sum or the difference of derivation of this, of the divergence of these derivations, and also the formula for divergence of the commutator of two derivations. And the next lemma about the Euler derivations. We will use this lemma by proof of the theorem 2. Here the first equality is the known Euler identity from mathematical analysis, and divergence Fen equals m plus n of f, where f is homogeneous polynomial of degree m. And here also some results of representation theory of semi-simply algebras. Let G be a semi-simple finite dimensional semi-simply algebra over an algebraically closed field K of characteristic 0. Let H be a Cartan subalgebra of G, and let phi be its root system and delta the basis of phi. Denote by B of delta the Borel subalgebra of the Lie algebra G. In the following lemma, we gather some essential facts about finite dimensional modules over the Lie algebra G. And let V be a finite dimensional module over semi-simply algebra G, then the module V contains at least one maximal eigenvector of the highest weight of V, a vector V, such that x alpha V equals 0 for all x alpha in G alpha, alpha in phi, and alpha positive. And HV equals lambda of H of V for all H in H. If the module V contains a unique maximal vector up to non-zero scalar multiples, then V is an irreducible module. And then third statement is almost obvious. If U and V are irreducible non-isomorphic G modules, then the module A plus direct sum plus V has only three proper submodules, U, V, and 0. And the next lemma shows what is the candidate to the maximal vector related to the chosen parallel subalgebra of SLNK. Its proof is rather technically complicated. Note that in case n equals 2, that is for the Lie algebra W2 of K, the proof can essentially be shortened. Lemma. Let D in Wn to M is greater or 0, 0, be a homogeneous derivation of degree M such that x alpha partial derivative d by dx beta d equals 0 for all alpha less beta and in these limits from 1 to n. Then d is of the form. Note that in general the form of d can be arbitrary, but in this case we see that d is of very special form for some coefficients c to 1 and ck to I. And the main result theorem lets the Lie algebra W and K be written as the direct sum of homogeneous components Wn, Wn to minus 1, Wn 0, and so on. And then L is a subalgebra Wn, L is isomorphic to the general linear algebra GL and K, and every sum of the sum is a finite dimension module over L. Every L module Wn to M, M is greater or equal 0, is a direct sum of two reducible submodules, MM and NM, where MM consists of divergence-free derivations, and NM consists of all the derivation from W and M that are polynomial multiple of the Euler derivation, En. And as a consequence of the main result, here is the next proposition. Let Wn be the decomposition of Wn into direct sum of homogeneous components of the standard grading on Wn and is greater or equal to. Let Wn equals Min and I, where Mi are reducible submodules of Wn0 from theorem 1. Then the next statements about dimension of these components. This is some trivial facts from discrete mathematics, combinatorics. And if St are submodules of Wn0, Wn, then St also is a submodule Wn, and Mi, product Mi and Mj equals M I plus j for all ij greater or equal 0. The same is true also for submodules I and j. The product of I and j equals I plus j for all ij if I is different from j. And the product Mi and j equals Wn I plus j for all ij greater or equal 0, except the cases. Here are 3 cases. And the last statement about multiplication of these submodules, the Wn to minus 1 and j equals Wn j minus 1. All these statements are consequence from the main result from the theorem 1. And once more consequence, let W and Wj be homogeneous components of the standard grading Wn, then the next equalities are satisfied. Wn I and product of Wn_i and Wn_j equals Wn I plus j, except the case I equals j equals 0, where this product equals ln k, only the submodule m0. And the next proposition shows what is the structure, structure of these submodules mi and nj. Let Wn_i equals mi plus ni be the decomposition of a Salenka module Wn_i into direct sum of reducible submodules, as in theorem 1. The modules mi and mj are non-isomorphic if I does not equal j. The same is true for modules ni and j. The module mi and j are non-isomorphic except the case of submodules mi and I plus 2 of the SL2 module W2, only in case when n equals 2, when mi is isomorphic to n plus mi equals ni plus 2. These SL2K modules are also GL2 of K modules, but they are non-isomorphic as GL2K submodules of W. And the subalgebra Wn0 of the Lie algebra Wnk is contained in the subalgebra Wn minus 1 direct sum Wn0, which is isomorphic to the linear affine Lie algebra Fnk. It is semi-direct sum of the vector space K to n and the Lie algebra GL and K. General linear algebra. This Lie algebra is a semi-direct sum of GLV and the abelian LBV, is the natural action of GLV on V. Note that the Lie algebra Wn to minus 1 and direct sum Wn0 is not maximal in Wn of K because it is contained in the subalgebra of Wnk consisting of all derivations with constant divergence. Nevertheless, the subalgebra Wn0 plus Wn minus 1 Wn0 has some properties similar to those of maximal subalgebras of Wnk. Theorem, the next theorem, theorem 2, let L be the direct sum of two components, Wn to minus 1 plus Wn0 be the subalgebra Wn and is greater or equal to, consisting of all the derivations with degree of fi less or equal 1. An element d, which is the sum d minus 1 plus d0, d1, and dk, di in Wn_i, and k is equals 0 or greater or equals 1, with dk is non-zero, it generates together with L the entirely algebra Wn if and only if the divergence of d is non-constant and either k is greater or equal to or equals 2, and d1 is not proportional to the Euler derivation En. Non-proportional by polynomial scalar. By a polynomial scalar. The proof of this theorem is based on the main results, theorem 1, and is not obvious. As a corollary, we get the next result belonging to Vladimir Bavula, a proposition from his paper. The set WC of all derivations from the algebra Wn and is greater or equal to with constant divergence is a maximal subalgebra of the Lie algebra Wnk. Note that the question about maximal subalgebras of the Lie algebra Wnk is in general a very hard problem. Some results were obtained by Rudakov, but his results are published without any proofs, but in the case n equals 0, such maximal subalgebras are described by recently in some papers of others. We studied model structure of the Lie algebra Wnk only for n is greater or equal to, or is subalgebra W0. The obtained results can be applied. Here 0 is here. The obtained results can be applied for constructing some maximal subalgebras, and also for better understanding the subalgebra structure of Wnk. Note that in case n equals 1, for the Lie algebra W1 of k, our approach does not work, since the module structure of Wnk is quite trivial. The subalgebras of W1 of k were studied in the context of the Virasoro algebra, which is a central extension of the Witt algebra of all derivations of the Laurent polynomials in variable t. Recently, Bell and Buzaglo, in their paper Maximal Dimensional Subalgebras of General Cartan Type Lie algebras, described all infinite dimensional subalgebras of W1k. This paper, in turn, is based on deep results by Petukhov and Sierra in their paper Poisson's spectrum of symmetric algebra of the Virasoro algebra. Thank you for your attention.